Hey everybody, today we're going to cover an example from the book titled Deep Learning with Python by Francois Chollett. I hope I've done his name justice. It's from chapter 2, and what we will be doing is classifying handwriting samples from a famous database called the MNIST dataset. And I'm going to walk you through the code. This code is taken from chapter 2 of Deep Learning with Python, and what we'll do is be classifying a set of handwritten numbers. Some history on this is that I think it was Stanford University, a group out of Stanford got a bunch of high school students together and they wrote out numbers 0 through 9. So there's 10 categories or classes within this group, and there's 70,000 samples. So what we're going to do is create your first model, and then I'll walk you through kind of the thought process on this model, and we'll start learning the anatomy of a neural net, the anatomy of how to build and the nomenclature associated with machine learning algorithms. So let's do that. So the first thing to realize is that I'm in a Jupyter notebook. Actually, the title of my Jupyter notebook here is 01 Chapter 2 Chollett 1 Walkthrough. And so you should be able to download that. So let's get started. So the first thing I did was import some important Python modules, NumPy, TensorFlow, and Keras. Now, an important thing to appreciate about Keras and TensorFlow is that Keras is a high-level API, application programming interface, that sits on top of TensorFlow. And TensorFlow really gives you the performance, parallelization, and underneath it is different hardware architectures. So what's nice about developing applications in Keras and TensorFlow is that you can target different processors. So you can run it on your laptop, you can run it on a GPU, and we'll do this later in the semester. You can run it on GPU servers through Google Colab, and even tensor processing units. And later in the class, we will use an NVIDIA GPU and deploy applications on a GPU as well. So it's important to realize this is architecture, and what we will be doing is using the Keras module to be able to build different machine learning algorithms and applications. So the first thing that I'm going to do here is notice here that I loaded up something called the TensorFlow Keras dataset import MNIST. And MNIST is this famous database that is handwriting images, and let me show you what they look like. Here is a sample of the images, and they're handwritten, black background on white. And for this exercise, we're going to extend it by asking you to actually create your own handwriting in Microsoft Paint and save it off and use it and use the model to predict the number that you've written. So that's an example of what the data looks like. A really important concept here is I'd like to first cover is that we've loaded the data. And so this is a function that's a part of the MNIST, when you implement the MNIST import. And then what it's going to do is divide up the data into training images and test images associated with their labels. And the label you can think of as the Y value or the category of the object. So the label for 5 here, the written 5 is a label of 5. The training data set itself is a 28 by 28 pixel size of the image. And you can see the details. 0 is the background, and then here is the value from 0 to 255, representing the grayscale level of each of these images. So, and each of these images are 28 by 28, which is not a very large size image at all. And so for learning processes, for educational processes, this is a nice library because we can, our data set, so that we can operate on it and it doesn't take a lot of computational power. So let's do a couple of things here. What we typically do in a machine learning application is we load in the data and then we split it up into what we call a training set and a validation set and a test set. Today, I'm not going to use the validation set, I'm going to use a training set. And then once we create our model, we're going to test it against the test set to see how good our model is, how accurate our model is. And why this is divided up into 3 sets like this, when we develop more advanced models here soon, we will actually do a training set, a validation set, and a test set. And then while you're developing the model, you'll test your model versus you use the training set to do the learning, and then you'll test it against a validation set, and you'll iterate. And what happens, it's by adjusting the parameters, it's called hyperparameters in the model, some information will leak back into the training set because you're human, and you'll maybe over-optimize the model specifically to the validation set. So you want to have a test set reserved. This is a never-before-seen set of data to ultimately test your model against. And so that's the logic of why you do 3 different groups of data: training set, validation set, and test set. For simplicity today, I'm not going to do a validation set. We will train, and then we'll see the accuracy versus a test set. So a little background. One of the things that you often do, first thing when you get your data, is to do some data exploration. So let's do some simple things here. If you run this and we print out the shape of the training images and the test images, notice that we have 60,000 images, and there's 784 is the shape. And actually, let's do this. Actually, let's run this. Got an old set of data around, and we're going to transform that in just a minute. But to start out with, we have 60,000 images, and they're each 28 by 28. So this is a tuple that's output by the shape function, and we have 10,000 test images that are 28 by 28. And if we think about this, what's the length of the training labels and the test labels? So the labels are the correct value of the image. So if we have an image of a 5, and then we need to know what is the actual value, that's called the label, and that is set up in our, is recorded so that when we load in the data, we get, for example, the test image and the corresponding known label. So that's what is meant by labels. So if we were to plot these images out and take a look at these images and display them, here's a label 5, label 0, and you can see that there's a lot of variation in the way that these images are written. So there's 60,000 training examples. And here's a new term, a class. There's 10 classes, so from 0 to 9. So there's a total of 10 classes, 10 categories you can think of it. And then each image has a dimension of 28 by 28 pixels. And then here's a list of the number of occurrences of each class. So the 0 has 5,923, 1 has 6,742, and so forth. So there's a good overview of what this MNIST data set looks like. Now if we dig in one step further and we plot out each pixel of the image, here's what a 5 would look like. And notice that the background is 0 for black, and white being 255, and then the grayscale images before are in between 0 and 255. So this is just a color map. We could have done this in grayscale, but we have a color map here, the default color map. Outputs kind of with a blue, violet background and yellow foreground. So the workflow for our application today is that we're going to feed the neural net the training data, the training images, and the labels, and then we're going to let the network learn. So it's going to associate the images with the labels, and what's going on in the background is the neural net will adjust the weights in the neural net to be able to accurately predict what image that we fed in to the network. And then we'll use the test images to verify the predictions that match the labels in the test labels. So we'll do the learning on the training set, and then we'll come back and we'll present test images and then see how accurate the model predicts the test images because we know the test labels. So let's import a few more things here and talk about this. So we're importing from TensorFlow Keras something called models, which is an object, and then layers. And these will be real critical in developing the architecture for our algorithm. And so we're going to create an object called network. Model sequential is a call that we'll make, and we'll create an object called network, and then we'll add to the network something called a dense layer of 512 neurons. We'll go into much more detail in the next few lectures, but this is meant to give you a high-level overview, solve the problem, start understanding the language of machine learning and neural nets, and then we'll go into the details for each of these particular items. So this is a dense network. It's 512 neurons in its first layer, and this next attribute here is activation equal ReLU, which is rectified linear unit, and we'll have a whole section on activation functions and talk specifically about the rectified linear unit. And then we have the input shape. In this case, this is the first layer. The input shape of the data is 28 times 28, and I believe if you multiply that out, it's 784. So we have 784 X values or features that will be loaded in to the first layer, and this first layer has 512 neurons. And then we will, the next layer will have just 10 outputs, because we have 0 to 9, and we'll use an activation layer called softmax. And softmax basically gives the probability, it'll rank the outputs from, in this case, of 1 to 10, with the highest probability being the predicted value for the test, for the training image, okay? So some important concepts here is that there's a loss function. When we run the model, we train the model, the loss function is like a cost function that we'll describe in later lectures. It's what the neural network is optimizing on. Just trying to minimize the loss from the predicted value from the actual value. And this loss is calculated based on the weights that are in the neural network. So this is how the network will measure its performance and on the training data. Then we can select an optimizer. An optimizer is the mechanism by which the network will minimize really the loss in the network. And there's several different techniques for optimization. The most common one that's introduced initially is called gradient descent. And in our method, we're going to use a technique called stochastic gradient descent as our first optimizer. And then the metric that we want to keep track of, in this case, we're going to select accuracy. And this is a monitor of how well our training and testing data, input image versus its label, does it accurately predict the value that was the label for the predicted image, for the image that was input into the system. So it's really the fraction of the images that were correctly classified. So an important point here is that the metric is really something for us to, humans to interpolate and interpret. And what the neural network will be using to optimize is the loss function. And they'll using a specific optimizer. Why is there more than one optimizer? Depending on the type of performance, the type of application, you can select a different type of optimizer. Okay, so let's get into this. Now, a final point here is that we can't pass in just any type of data into the Keras TensorFlow library. We have to basically form our data into the right array or tensor data. In this case, we're taking it from a list and we're going to put it into a float 32 array. So we're reshaping it first, and then we're building it into a type float 32, which is a floating point set of floating point values, and we're normalizing this to 255. We'll talk about that in the future. Is that most inputs or x values that are input into the network are normalized, and so that they're between 0 and 1. So instead of between 0 and 255, our data now will be floating point. It won't be integer data. It'll be floating point data that will input into the model. Okay, and we've done that for both the training data and the test data. And then finally here, we want to convert this to what's called categorical. And every time I see categorical, what I think in my mind is not binary. So a binary output would be, I've got two classes, 0 and 1, for example. In our case, we have 10 classes from 0 to 9. So we're going to, this basically means output the data, or not output the data, but make the data into 10 different classes or labels, okay? So we get ready to run our model, and what we can do here is we can change the number of epochs. I'm going to change this to 5 epochs, so it'll run really small. And then the batch size is 128. So you can think of, we're going to take 128 samples, one batch, from our 60,000 images, and then we're going to perform 5 iterations, or epochs. And we're going to input the training images, the 28 by 28 images, and the labels, and then we're going to, on each epoch, we're going to come up with a loss function, a loss output, and then our optimizer will do some optimization using gradient descent, reduce the loss, and hopefully improve the accuracy. So the accuracy is really a number for us to look at. So for these first this first epoch that I've run in the past, amazingly, 128 after 128 samples in the first batch, we were 91% accurate. So let's run this on 5 different epochs. And it looks like I haven't run all of my functions here, so let me go through this. So run this particular, show the output, import all my modules, compile up the model, convert to floating point and the right data type, ensure that we're looking at 10 categories. Now we're running the example. So we can see it's taking a while to learn. Each step took 5 milliseconds, and we're only going to run this 5 times, or 5 epochs. Notice that in this case that we started out with our first accuracy was 76%, second epoch level was 87. So for each, we knew the label of the image that we input into the system, And it, after one training set, it could predict at 76%. And by 5 epochs, we're up to 90%. Now notice that the loss is decreasing for each iteration. And so what we're striving for is not to overfit this model, and overfit, we'll get into a definition of that in the future, is that really you want to balance between fitting the model so you can generalize it on a new set of data, in this case will be our test images, and not just design the model to work just with the training set. So an overfit model works better for the training set than it does for your final test set. And so we want to strive to make sure that a model performs well, but is not overfit for the training data. It works just as well or even better for the test set. So what I've done next is let's run this analysis, call it network, and evaluate it on the test set data. Here, it's going to pass in the test images and the test labels, and then get the loss and the accuracy gets returned. And so now this is a different data set that the model has never seen before, and then we'll predict based on the 10,000 images what the accuracy will be. So we run that and it's 91% accurate, very close to our training and accuracy for our training data, which is very good. So the questions I'm going to ask you to answer in your assignment is, why is the accuracy lower on the test data than the training data, right? Something for you to consider. Create your own test image, and let me show you what a test image would look like. And here's a test images in Microsoft Paint. Now notice this guy is 100 by 100 pixels, so you're going to have to reduce it down to 28 by 28. So create a couple of test images. I believe I asked you for a 4 and an 8, and you can rotate them. And we'll have the assignment goes into details. And so the assignment that you have on Canvas is specifically the task, but this is a high-level questions I'll be asking you for. So please look at Canvas for the final assignment. And then ultimately describe your findings and why the model is accurate or not accurate on the new test images you created, the 4 and the 8. And so that will be an interesting discussion, and we'll talk about that in office hours. All right, until next time, thanks.